So we can resume this morning session by a talk of our host, Abhishek Dhar, who will be talking about energy current fluctuations in one-dimensional equilibrium, in ring geometries in one dimension systems. And thank you, Abhishek.
Okay, so first of all, I would like to apologize like before the start of the beginning of the talk. Like this talk is going to be a bit disorganized. I mean, being the organizer of the workshop, I have not had time to organize the talk, so it's going to be disorganized. But I will try to convey the main message of the thing. So this is looking at energy current fluctuations in in ring geometries in systems with Hamiltonian and also stochastic dynamics. Okay, so this work is done with KG, who is here, and Bernard Derrida and Anjan Roy. Anjan Roy was a student, former student, who is now in Max Planck Institute, Potsdam. Okay, so let me first explain what the basic question is. So we are looking at, so let's say, so we are looking at a system of particles moving on a ring, and I'll discuss two models. So one model is the so-called alternating mass gas. So this is just a system of particles. So this is on the continuous line. Okay, and they have masses ma. Okay, so masses are alternate, and so the system is described by positions of the particles and moment of the particles. And let's say I have 1, 2, n particles, and the total length of the ring is L. Okay, and the dynamics is completely Hamiltonian. So they just move ballistically and then they collide elastically. Okay, so they move with constant velocity and then collide plus elastic collisions. Which conserve okay, so this is the dynamics. Okay, so the reason that we make the masses alternate is that is that if they were all equal masses, then the system is very kind of trivial. Okay, so then when they collide, they just exchange velocities. So this problem was discussed in the context of tagged particle diffusion by Sanjeev. So that is kind of integrable model, and nothing much interesting happens when we look at energy fluctuations. But this model, where if you make the masses alternately different, then it's a non-integrable model probably, and it has good ergodicity properties and so on, and it's a good model to study like thermal transport and so on. Okay, so this is the model we study. And so this model has been studied in like open geometries, where you put heat baths and then look at what is the heat current, how does it decay with system size, and people find anomalous transport and so on. Okay, so what we look at is on this ring geometry. So it's a equilibrium system. So we prepare the system in equilibrium and then look at energy current fluctuations. Okay, so let's say I take some fixed position y on this ring, and I ask what is the heat current that passes through this point in a given time. Okay, so I can define the heat current. So in this model, the heat current at the point y at time t is so it's easy to see that this is basically given by Okay, so this is the heat current at time t, instantaneous heat current at time t at a position y. Okay, and what we'll be interested in is this object, the integrated heat current over a given time interval. So 0 to tau. Uh, Cube. So this the energy density would be square, and then if you take a derivative and write a continuity equation, you will get something like this. Okay, so this is the total heat that passes through point y at in a time tau. So equivalently, one can look at the total. So one can integrate this object over the entire length of the thing, and then I could look at some object like q equals to 1 over length. So this is now a function of y. Okay, so I could also look at this, and okay, and then what I'm interested in is the statistics of this. So this is a, so what I do is I prepare the system in equilibrium, and then ask like what are the, so then this, if I measure this object starting from different equilibrium configurations, then this is a fluctuating object, and I am interested in the statistics of this. Okay, so this is what I call current fluctuations. Okay, so what do this look like? Okay, so what I'm interested in is basically looking at these cumulants, either QNC or QNC. So these are expected at large times to behave in the same way. So these cumulants, and more generally, I would like to consider the cumulant generating function given by this. Tau, right, yeah. So this for large tau. Right, yeah, that's what we want. Large tau, and this average, okay, so this I should say, this average is done with respect to, so what we do is prepare the system in a microcanonical ensemble with zero momentum. Okay, so average over microcanonical initial conditions. Okay, so momentum is strictly, total momentum is strictly zero. Fix the volume, right, yeah, fix the length, right, yeah. Okay, so now this problem was, I think, first looked at by in this paper. So Brunet, Derrida, and Gershenfeld in this EPL 2010. So they numerically studied, looked at this cumulants, and so basically they could look at Q square and Q4. So they just did simulations and obtained these objects. And so what they found is, so then one of the things they looked at is how do these cumulants scale with system size, right? So what they found is that the second cumulant, this okay, so the first thing is that all of this scale with tau. Okay, so so basically we'll look at, so all cumulants scale with tau, and so basically we'll divide by 1 by tau and look at the limiting behavior of this quantity. Right? And then we ask how does this depend on scale with system size. Okay, so what they found is that this scale says 1 by L to the power half, and this scale says L to the power half. Right. Okay, and sorry. Capital Q is the like you. So small q is like you look at the current through a given point. Capital Q is like you integrate over all. Over, yeah. So you look integrated over all y. Right. Yeah. Which is for small q? No, there's no 1 over tau. It's just this. It's the total current. Total. This is the total current crossing a given point in a given time. So Q average would definitely scale with tau, right? Like the total current should scale with tau, and you find actually all cumulants scale with tau. No, on average, there's no current because this is in equilibrium state. So, right. So actually, Q average is strictly zero in this. So only the even cumulants are non-zero. Okay, so this is what they found. So just to compare, like if you had a diffusive system, then in fact one knows exactly like how these cumulants behave, all cumulants behave. So for a diffusive system, so diffusive system means something like where you expect Fourier's law to be valid. For example, it's still heat conduction, but where let's say Fourier's law is valid. So in that case, what you find is that Q square goes as 1 by L, and any other even cumulant goes as I think 1 by L square. Okay, so these are all divided by tau, and these are the asymptotic large tau limit. Okay. So this is completely different, right? I mean, the cumulants, I mean, in this system, the higher cumulants actually blow up with system size, while here it actually decays with system size. Okay, so the current fluctuations in these anomalous systems with anomalous transport and diffusive systems are completely different. Okay. So this is what was known in this from this paper, and then so at some point I and KG were discussing with Bernard, and he suggested that is can one understand these results in the framework of fluctuating hydrodynamics. Okay, so that's what mostly I'll try to explain, like some attempts that were made and also some. So my talk will has three parts. So we have some. There are some numerical results. On two models. One is the alternating mass hard particle gas. Okay, and second model, which is what I call the momentum exchange model. And for a harmonic chain. Okay, so this model is just what I just wrote, and this model is what Stefano had introduced last week. So this is a model where you have a lot of exact results, and it is also momentum conserving, energy conserving, and it's different from this in that like it belongs to a different universality class in the framework of what this fluctuating hydrodynamics. Okay, so therefore we want to see if there are some differences for moment like current fluctuations in these two models. Okay, so there are some numerical results, and then basically trying to understand whatever we see in the framework of fluctuating hydrodynamics, fluctuating hydrodynamic theory, and then if I have some time, I'll also present some sort of more heuristic arguments in terms of a model of Levy-Walkers. Okay, so which also kind of explains many of the numerical results that we see.
Could you explain what the second model is?
It's a harmonic chain, and you have momentum conserving and energy conserving noise. So you just exchange like the velocity, you randomly flip nearest neighbor velocities with some rate.
On a ring.
On a ring. So again, it's okay. So let me just write the model. So this is model one, And okay, so these are all equal mass particles. So this is harmonic. So the dynamics is I mean partly Hamiltonian. So this is so the dynamics is there's the usual dynamics of a Hamiltonian dynamics of for a harmonic chain, plus you add stochastic noise. Which basically takes the momentum and between nearest neighbor particles and exchanges them with some rate gamma. Right, I hope the model is clear. Okay, so for this model, one has a lot of exact results. So and it belongs to a different universality class than this model. So that's why we want to see. I mean, how current fluctuations look. Okay, so this is model 2. Okay, so now let me use the slides. Okay, so okay, so what I'll do is I'll maybe there are some people who for whom this might be useful. I just give a very brief introduction to anomalous heat conduction in general, and then I'll again let's recall the some basics of fluctuating hydrodynamics. And then I'll tell you what results we have on these energy fluctuations. Okay, so this is the usual problem, like Fourier's law of heat conduction is given by something like this, and if this is true, then it implies that basically like if you have a small heat pulse somewhere, it spreads according to the diffusion equation. So proving this is a challenge. I mean, it's an open problem. Like, can you prove this starting from complete microscopics? And the problem of anomalous heat transport is that in at least in one-dimensional systems, you find that if systems with momentum conservation, kappa actually is not an intrinsic property of the system, but it scales with system size. Okay, and basically it diverges with system size as size to the power alpha. So it's not an intrinsic material property, and this you can't even write this equation. Okay, so how do you check the validity of Fourier's law for a system with some specified Hamiltonian dynamics? So one way to do is to take any model, like for example these two models. I could take them on open system, like open geometry. I could connect heat baths and then just measure the steady state current, and then see how this current scales with system size. Okay. So I mean, there are some cases where you can do this exactly. In most cases, you have to do this on a computer, and then you see how the current scales with the system size. If Fourier's law is satisfied, it should scale as 1 over L. But what you find is that it doesn't scale as 1 over L, and the conductivity can be defined as J times L divided by delta T. And if you define it this way, and the current does not scale with 1 by L, but it's slower decay, then you find that the conductivity goes as some power of alpha. Okay, so here are some like typical simulation results that you would see. So this is another model that is also studied a lot. This is the Fermi-Pasta-Ulam chain. So there's a kinetic energy of n particles, and then you have some nearest neighbor interaction, which has a square term, a cubic term, and a quartic term. So this is usually sometimes called the alpha beta FPU chain. So for this system, you can connect two different temperatures at the ends, and you'll get some temperature profile like that. And if you measure the conductivity as system size, then you find that it never saturates. It keeps increasing with system size. Okay, so this is like one of the better simulations where everything looks clean, and you get a power which is n to the power 1/3, which is what you expect from various theories. Okay, so this seems to be a generic feature of momentum conserving systems in one dimension. Uh, okay, the other way you could look at anomalous transport is to note that the conductivity is kind of, okay, so this is not an exact result, but kind of you expect at least from some sort of uh, linear response arguments that the conductivity is given by correlations in equilibrium. Okay, so you look at current correlations in equilibrium, and that should give you conductivity. And then what you find is that in this systems with anomalous transport, this kind of decays very slowly, and it's not integrable. So therefore, that also indicates that this object diverges in these systems. The other thing one could also look at, which is what this theory of fluctuating hydrodynamics does, is look at like how energy fluctuations decay in equilibrium. Okay, so basically you look at some like in equilibrium, this sort of correlation functions, which basically tell you that if there are spontaneous fluctuations, how do they decay? And for a diffusive system, they should decay like Gaussian, but you find that they decay in a super diffusive way, and so they spread much faster. Okay, so that also tells us that transport is anomalous. So these are things you can do for a system in equilibrium and also and still say something about anomalous transport. So either you can do a non-equilibrium study or this sort of equilibrium studies and say something about anomalous transport. Okay, so most analytic approaches are based on looking at this equilibrium correlations. Okay, so I just want to say that I mean there are a lot of very puzzling things like, for example, if you look at the alternate mass case, so there's some like recent numerics where you look at conductivity for system size for very large systems. Okay, and so what these plots give is results for different mass ratios. Okay, so what you expect that is that things should be universal and not depend on mass ratios and so on. But here what you find is that as you change the mass ratio, it's not clear that, okay, so what you expect is that at sufficiently large system size, you should get the same n to the power 1/3 divergence. But at least in numerics, sometimes it's kind of difficult to verify this. Okay, so this plot corresponds to a case where the masses are very close to each other. So m1 by m2 is very close to 1, and you seem to say it looks like the conductivity is going to a finite value. Unlike this case where you get some power into your 1/3. Okay, so there are some still lot of open questions in this field. Okay, so now let me talk about fluctuating hydrodynamics, which basically looks at systems in equilibrium and looks at decay of space-time correlations. Okay, so the first thing that one does in this theory is to identify the conserved quantities. So for this kind of models, there are three conserved quantities, at least three known conserved quantities, and these are basically so this is one of the concepts. It's the stretch variable, just the distance between nearest neighbor particles. So this is kind of like density. Inverse of this is just density. So either one can talk of density as the conserved quantity or stretch. Then there's momentum and energy. Okay, so then you just write the exact conservation equations, and then what you do is basically look at fluctuations around the equilibrium values. Okay, so now we look at, yeah. This right here. So right, yeah. So yeah. So that's a good point. I mean, here I am defining like space coordinate. In this case, I will mostly talk of Lagrangian coordinate. In this theory, I am of course again talking of a Lagrangian Lagrangian Euler. What I don't know. Like it's. That's all. No, is it? Okay. So this is like the x here refers to the tag on the particle. Okay, it's not a fixed position in space. Okay, so yeah. So then what I do is expand these fields around their equilibrium value. So I have a system in equilibrium, which means there's some temperature and pressure, and corresponding to this temperature and pressure, I have some expected values for the average energy and average extension. So the momentum is always set to 0. Okay, so I have some average extension and average energy density, and then I expand, look at fluctuations around those values. Okay, so this u1, u2, u3 are the fluctuating variables of the conserved quantities, and then basically one comes up with some sort of this sort of hydrodynamic equations. So these two parts are basically obtained by just expanding the equilibrium currents around the equilibrium, these currents around the equilibrium value. Okay, and these two parts, this is kind of a dissipative and noise parts, are just added phenomenologically to kind of model the I think the dynamics at a shorter time scale where things are being which take the system to local equilibrium. Okay, so there's some sort of phenomenology going into in writing these equations, but this is what one starts with in fluctuating hydrodynamics, and then one can make based on these equations you can compute like what space-time correlations of these conserved fields will look like. Okay, so one of the things one does now is supposing I drop the nonlinearity, then it's just linear hydrodynamic equations, and I can go to kind of normal modes. Okay, so if I look at the normal modes of the system, what I'll find is that there are two like propagating sound modes going in the opposite direction with speed c and minus c. We see the speed of sound, and one diffusive heat mode. Okay, so at the if I don't have the nonlinearity, then if I look at correlations, they're obviously Gaussian, and what I'll find is that the two of the correlators move like with the speed of sound, and one just sits at the origin and spreads diffusively, which is the heat mode. Okay, so I have these three modes, and then one can so then in this normal mode picture, what one can do is then include the nonlinearity. Okay, so let me just write down the Okay, so what I said is one has these basic fields u equal u bar equals to, and then one makes some transformation and constructs this new fields phi equals to phi plus, phi 0, phi minus, which is some transformation on this object Ru. And then I have some equations for the fields phi, and so at linear order the equations for phi plus minus look like and okay, so this diffusion constant and this the strength of the noise are related by a fluctuation dissipation relation, and these are not determined by the microscopic model right now. This speed of sound is determined completely by the Hamiltonian. Okay, and okay, so these are the linear equations, and then you try to look at the nonlinearity, and what you find is that if you look at the alternate mass model, then the leading nonlinearity here is basically g square. Okay, so this is the leading nonlinearity, and then you have like phi plus, phi 0, phi plus, phi minus, and so on, which are expected to be of less important because these modes are moving away, right? So this is the leading nonlinearity, and for the heat mode, what you find is that it's not, you don't have a phi 0 squared term, but instead what you have is so I'll just call it G. Okay, so the heat mode doesn't have a phi 0 squared term. It depends on the sound mode nonlinearity. Okay, so this is the leading nonlinearity for the heat mode. Okay, so now the sound mode, if you look at it, it's basically like it's exactly Burger's equations, and so you can make predictions for like for the correlators phi plus phi minus. So this is just exactly the KPZ scaling function. For the sound mode, you take this solution of the like take the solution from this equation and kind of plug it in here, and then what you find is that the phi the heat mode correlations have this Levy form. Okay, so this is the main prediction from one of the main predictions from fluctuating hydrodynamics. Okay, so the other point is if you have like for the momentum exchange model, if you do this, then what you find is that you don't get this term. So this goes to this, this is not there. So which means that the sound modes are completely diffusive, right? So the sound modes are completely diffusive, they do not have KPZ scaling. And then if you put it here, you will find again Levy distribution, but with a different exponent. Okay, so those are the main predictions. Okay. No, C just means it's just linear term, right? So it just moves with constant speed, but it spreads diffusively. Right, yeah. G non-zero tells you it's diffusive. G just comes from the nonlinearity. In the alternate, yeah, I mean, like you just write the equilibrium equation of state, and from that you can, by expanding things in the fields, you can just find what G is. For any given model, you just find the equation of state, and then from that you can basically compute this matrix G. No, non-zero G. This is just the Burger's equation. Okay, so then you just use known results, and okay, and there you can also do mode coupling theory and again get these results. But I'm just at a zeroth order level. You can just think of this as Burger's equation. This is exactly Burger's equation, and then you exactly expect those in the long time limit. Yeah, that's not diffusive. So if the functions, the scaling functions are this KPZ scaling function. It's not a Gaussian. Okay, so now this is what one knows for equilibrium correlations. So now what we want to do is, can one use this also to compute current fluctuations? Okay. So let's see what. Okay, so I just want to show like some numerics we did to check like this theoretical results. So this is what I said, like there are these three correlation functions, the sound, the heat mode, and the two sound correlations. So so these are the how these three. So this is the heat mode at three different times. So I mean this is the earliest time, and then it sorry, the rate is the earliest time, and then it keeps spreading. These are the sound modes. One goes to the left with speed of sound, and this other one goes to the right with the speed of sound. Okay, and then one can kind of check whether these relations are satisfied. Okay, so you shift the sound modes by a distance c of t, and then do the scaling and see if you get a scaling collapse. Okay, and this is what we find. So for the sound mode, it's you can see that this is a KPZ scaling function, and everything works out. So red one is the earliest time, but at later times you get a very good collapse. And even the scaling parameters between theory is predicted by the theory, and they agree quite well. Okay, and for the heat mode, again you find very good agreement with the Levy distribution. Okay, so now let's look at current cumulants. Okay, so now the main point that the first thing that you notice is that the heat current. So this is in normal coordinates. I wrote the heat current. This is basically the heat current in normal modes. But even if you go to the original variable fields, you'll find that the energy current is basically given by this difference of these two KPZ fields. Okay. So therefore, I mean, then what you can immediately say is that the heat current cumulant generating function is basically the difference of two KPZ currents. Okay, so I mean, just by using this. Okay, so the main observation is that the heat current is a difference of, so there's some constant, but it's difference of these uh, two currents, each of which is the current in the original Burger's equation, right? So therefore, if you write the cumulant generating function of this object, right, so this is the integrated current, then it's basically, it's just the difference of these two currents in the Burger's equation. Okay, and this is known exactly because of, so there's a paper by Derrida and Lebowitz which computes the current fluctuations in the asymmetric exclusion process, which is related to current fluctuations in the Burger's equation. So one can just take those results, and so basically the cumulant generating function for heat energy current fluctuations in the alternate mass gas is, so what this is a conjecture, is the sum of the cumulant generating functions for Burger's equation with just, I mean, these are independent fields, so it's just mu of lambda plus mu of minus lambda, right? So now for the Burger's equation, there's an explicit form for the cumulant generating function, and using those, so because of this mu of lambda and mu of minus lambda, the odd cumulants all vanish, and for the even cumulants, you have this explicit, you can compute all cumulants, and this is what you find. Okay, so you can see that the second cumulant indeed goes as 1 by root n, and the fourth cumulant goes as n to the power half, and the third cumulant goes as n to the power 3 by 2. Okay, so I'll show you some numerical results. So here what we do in the numerics is basically, so this is second cumulant, fourth cumulant, and sixth cumulant, and so these are q square divided by tau plotted as a function of 1 by tau. So as you go to large tau, it asymptotes to some quantity, okay? And the blue and red quantity are basically for small q and capital Q, which I defined. So asymptotically they go to the same value as is expected. And so then what we do is basically we extrapolate these lines to their, where they are expected to meet, and then take these values and plot them as a function of for different system sizes. So this is for a given system size. So we do this for different system sizes and then plot as a function of n, and indeed this is what we see. So second cumulant goes as 1 by root L, and fourth cumulant as L to the power half, and the sixth cumulant goes as L to the power 3 by 2. Okay. So these two results agree with what was obtained earlier by in this paper, and this now fits with what we expect from the theory.
Abhishek?
Yeah.
Do they have the coefficients? Did they have it in this?
In the, yeah, you can get the using from the, yeah, you know the coefficients exactly. Okay. Yeah. So the other nice thing is that if you take the ratio of like C2 into C2 into C6 divided by C4 square, that is independent of any parameters. Okay. So that's a universal constant equal to around 3 point something, and we try to check whether it does converge to that. So it's 3 point something, but it still doesn't go to that value, but it's kind of close to it. This ratio. Okay, so this is for the alternate mass gas. The other case we looked at is this exchange model, momentum exchange model, in which case, as I said, there's no nonlinearity in the sound in the sound modes, right? So therefore, if I want to compute this object, I mean it's a completely Gaussian problem. So that one can obtain again just compute exactly. So for the momentum exchange model, the heat current is given by difference of these two sound modes. These are linear modes, and so one can just has to perform some Gaussian integrals and get the cumulant generating function. So here again, from the cumulant generating function, you can obtain all the cumulants, and what we find is that The second cumulant is independent of system size. The fourth cumulant scales as n square, and the sixth cumulant as n to the power 4. Okay, so this is completely different from, again, this all these models. Okay, so the cumulants actually grow very rapidly with system size, and I'll just show some numerics that we obtained. This is for the momentum exchange model. So in this case, somehow it's very hard to do numerics for very big system sizes. So far we have done only like 64 sites, and you see this n to the power 0, n square, and n to the power 4 scaling. Okay, so right, so that's the sort of the main story. That if you just use fluctuating hydrodynamics, it seems to work quite well, and you can get predictions. Okay, so now let me just say that there are some problems which makes one a bit uncomfortable, which is that usually when one looks at fluctuating hydrodynamics, one of the important things is that the sound modes and heat modes get separated, right? So if one is looking at an infinite, like a very large system, then you look at timescales where they don't interfere. But now we are on a ring geometry, so clearly the sound modes and heat modes are going to interfere after some time, and so maybe, I mean, one should actually take into account the coupling terms. So that's one reason why it may not, it could not have worked. Okay, so that's one point. Okay, so okay, but the reason that see, even on a ring, so even on a ring, okay, so let's say you have this heat mode and the sound modes. So they go around and then they start interfering, but then because they are traveling at the like sound speed, their overlap is for some short time. Okay, so which is one reason which maybe it still works. Okay, and okay, so okay, so then we have another, like I said, there's a third way of understanding these results using this Levy-Walker's model. So the Levy-Walker's model is kind of a completely phenomenological model where you basically think of the energy being carried by not by random walkers but by particles which do a Levy walk. Okay, so a Levy walk is something where you walk with a fixed velocity for a time which is chosen from a power law distribution, so such that the first moment is finite and the second moment diverges. Okay, so it's not the same as the Levy flight. Okay, so for this model, okay, I think okay. I still have 2 minutes, so I think I can. Okay, so basically you just think of the energy being carried by these Levy walkers. Like each walker is carrying an energy packet, and then you have like n walkers, let's say n independent walkers moving on this ring. Okay, and you ask you ask for the current fluctuations at a given point. Okay, so with this Levy-Walker's model, first I want to point out that in an earlier work also with KG and Derrida, we had shown that you can recover many results of anomalous transport, including like temperature profiles and dependence of current on system size and so on. So then we also try to look at current fluctuations using this Levy-Walker's model. Okay, so basically, as I said, you have independent walkers which jump, which go with a constant velocity for a time t, which is chosen from some distribution which has a long tail. Okay, so t is chosen from a distribution which has like one at long times. It looks like 1 plus beta. Okay, and this beta is related to the divergence exponent alpha. Okay, so now if it's doing this, it can go either this way or this way, and you ask how much current goes through a given point. So then if on the open line the displacement in time t of the Levy-Walker is x, xt is this the displacement starting from the origin, then the current should just be xt divided by L. This is the number of times it goes round the ring. And if I want to find cumulants, I just take to the power n cumulant, and then there are n particles, so I multiply by n. Right. So, so current cumulants are basically given by this if I use the Levy-Walker's model. Okay. So now the question is I just need to find xt to the power n given that each step has this distribution. Okay. So now if you do this, what you'll find is that this actually doesn't scale with time because of this fact. So there's a problem. So then what one needs to do is then one needs to put a cutoff in this distribution. Okay. So then one says that there's a cutoff like tau of c, which depends on the system size. Okay. So what you imagine is that if you are in a finite system, then the Levy walk has to be cut off by some length scale, and and it depends on system size in some way. Okay. So now what is this exponent delta? Okay, so in our original paper, we had made various guesses on what this could be. It could be 1 just because it's the system size. So one possibility is like delta equal to 1. The other possibility is like if I look at so this Levy walk at some time scale, it basically looks like in momentum space, it looks like. So the distribution, if I look at how the distribution spreads and then look at the Fourier transform, it basically looks like a Levy stable distribution. Then if I put k, the lowest frequency wavelength is like 1 over L. So from that I can pick out extract a time scale. Okay, so from this I would get a different time scale, and I think delta would be like. So basically what I'm saying is I would put k, the lowest wavelength is 1 over L. So 1 over L to the power nu t is like order 1, and so time scale would be like L to the power nu. Okay, so delta is just this nu. Okay, and okay, so given this cutoff, now you can calculate this object, and then you will find that this actually scales with tau, and you can extract the how the different cumulants, what the different cumulants are. Okay, so then if you use this, it turns out that both of these don't work. Okay, what works actually is like if you say that the time scale is actually controlled by the sound mode. Okay, so there's some time scale over which the sound mode is expanding. Okay, and then if it like completely fills the system, then there's a strong interaction between the sound and heat mode. And if you use that, then the time scale that you get, if you put that delta, then you can recover all the cumulants that you see. So both for the momentum exchange model and for the alternate mass gas, you get complete agreement with all the cumulants. Okay, so I hope I conveyed some sort of message. I'm sorry for the disorganized talk, but this is not working, right? Sorry, it stopped. Oh, great. Okay, I was thinking this time. Okay.
What would be the physical argument to explain that this Levy-Walker's model is a good phenomenological description of?
Right, yeah. So in some sense, like if you look at the heat mode and look at like the correlations that you get for the heat mode, it's exactly Levy, right? So so in some sense, the Levy model, it's already kind of clear that the heat fluctuations decay according to a Levy. So then you might just try to imagine a microscopic model where the a random walk model which also produces a Levy distribution. So in that sense,
the index of this Levy is the same.
It's the same, right? Yeah. It's the same. Yeah. So there's some difference between the Levy distribution and what you get from a Levy walk, which is kind of important, I think. Like if you do a Levy distribution, if you take a Levy stable distribution and go to X space, like the real space, then okay, then it has like these long tails which go to infinity, right? But if you look at the real like the heat mode in like in your simulations or from the Levy-Walk model also, you'll find that there's actually a cutoff. Okay, so so in the Levy-Walk model, clearly you can't go beyond speed v times t. Okay, so then what you get is some like some feature at, so there's a power law tail, but it gets cut off at some like distance. Okay, so which you don't get from the Levy distribution, but the Levy walk has that feature, and also that's what you see.
Yeah, I'd like to comment. I think you can give physical interpretation to these Levy walkers. It's pairs of sound modes that carry the energy to a certain time or a certain distance, and they combine again into the heat mode, and then it gives off its energy either to a pair that goes to the left or a pair to the right. So it's really a random walk with some kind of distribution. But there is a subtle difference between current correlation functions, because there you are k0, so you combine sound modes that have exactly opposite k values, and there's no oscillating factor in the propagation. Whereas if you look at the heat mode decay, there is a finite k and you get oscillations. So that's why you get this t to the minus third also for the heat mode correlation function, which is the pure k to z behavior.
Right, no, so the Levy-Walk model, it's a purely, I mean, phenomenological model, but it.
You can get an interpretation.
Okay, you're saying there's an right, yeah.
The object transporting the energy holistically for some time. Combine again, another pair.
Right. Okay. Yeah. Yeah.
You also see that, for example, in Gauss simulations. For short times, you see, say, transport of energy over a distance ct, and that is ballistic. It's ballistic, so it's the first stage where you picked out this pair of sound modes, and before they have decayed, you see it really moving at ct. But at later times, because you get a combination of that goes this way and that goes that way, you don't see it.
Okay.
Actually, for the harmonic chain, the picture is actually correct mathematically.
Yeah.
There are the phonons that move with a certain velocity and they scatter
Okay.
k square. So for more k, that's the But what I don't understand is this cumulant, because the final process is the Levy process, which has infinite values. So these things that have to diverge. So what?
No.
Variance of the Levy process is just infinite.
But it's not actually. It's,
we draw a certain way, but.
Right, but that's yeah. So, but if you actually look, if you put a pulse and see how it spreads, it's not. The variance doesn't blow up, right? It grows super diffusively.
Yeah, it eventually grows, but it's a transitory effect. I mean,
No, but
at a certain moment.
No, like no, at any time it grows as t to the power something. Like for, I mean, it's.
Yeah, this doesn't say anything about the right time scale, which the process will converge to the Levy process.
Yes, but is yeah. So if you look at the, I mean, the actual distribution, it's Levy. Okay, I mean, like if you do some scaling, it's Levy on all scales. But if you just work with the original time variable, I mean, it's there's a speed of sound and it's completely cut off. So it has a finite variance, right? I mean, that's the real like times. I mean, I don't know. Like it's what the actual time where you calculate everything. And on that time scale, if you plot anything, the correlation functions do get cut off at the speed of sound, like c times t. And they will have a finite variance.
Cutting off in this calculation, cutting off the contribution of the two tails.
Of the two tails, right? Yeah, yeah. You need to. I mean, that's what you see in like. It has to have a finite. It can't extend to infinite, right? Unless you, I mean, if you rescale things in such a way, then of course it will look like it's going to infinity. But if you work with the original variables, like the real time, I mean, I don't know, like if you don't do the times and space scaling in the way in which you get the Levy stable distribution, then it has a finite cutoff.
What you see in reality, there is no real output. It starts oscillating and so it gets.
Right. I mean, it actually has an exponential decay at the tails. Like it really gets because I mean nothing can propagate. I think there's some like real bounds beyond which you can't things can't propagate. So yeah, that's.
No, I'm sure what you say is correct. It just doesn't come back to my mind that when you rescale the process, you converge to a Levy process which has infinite variance.
Yeah, that's also correct. But I think you shouldn't rescale the like then you lose some features. Like the fact that the actually if you put a pulse, it spreads in a the variance has a finite value which scales with time.
If you scale the process such a way that the variance stays finite,
right,
the process will just converge to zero. It's not because it's not the right time. If I rescale the time, what the parameter nu you find there for the harmonic case?
This delta. No,
the nu, the time scale. You said nu is the parameter.
Oh, for the harmonic case, if you use this, of course, you would get 3 by 3 by 2, right? Yeah, but that's right. Yeah.
Okay, so probably we're saying the same thing. The other thing is the difference between the Lagrange. I mean, at the end, you use the Lagrangian coordinates to compute the current.
The Lagrangian, you fixed on the particles, right? Yeah.
If you until you look expectation averages, of course there will be no difference since you took zero average.
Right. Yeah.
But if you look at variances and moments, then
there could be a difference.
Center of mass can have different contribution. You may have different values if you're using the current in the Euler coordinates.
Okay, so for the exchange, for the momentum exchange model, when we calculate currents also, it's in the Lagrangian. So both are in the Lagrangian frame because we just do between x and x plus 1.
I thought because at the beginning you wrote it in the.
So that was for the alternate mass gas. So for the alternate mass gas, that's true, right? We work in the fixed, like in the Eulerian thing. So there, of course, that question is valid.
Actually, cumulants can be different.
Cumulants could be different, right? So there, the question is right. Yeah, it could be different.
I guess for the momentum exchange model, when you compute heat conductivity, how does it behave? What is the parameter alpha? You have this L, L to the alpha.
Okay, so you're saying in a non-equilibrium simulation?
Yeah, I'm saying how you would compare with the non-equilibrium simulations, the computation you do from here, can you compute the heat conductivity?
No, so this is like, I mean, this is kind of the latest simulation that one sees. So for our mass ratio, you would get something like n to the power 1/3. This
but I'm talking for the momentum exchange.
Oh, the momentum exchange. So there you would get n to the power half.
You get n
to the power half in a non-equilibrium simulation. That's very neat.
And also it comes out in this model.
From this, from the hydrodynamic theory, also you get n to the power half. So that's one model where everything is consistent, right? Yeah.
Any other question? I had a small question about this picture precisely. Yeah. So you said that when the masses differ little, there seems to be...
Right, yeah, which is completely counterintuitive.
Yes, and when they are very different, on the contrary, you get the one time.
Yeah, again, there's like, I think it's not asymptotic, like it's not monotonous. If it's too different, then again you get something strange, right, yeah.
So do you have any intuition of what's happening in the very large time?
No, I mean, this is a big puzzle, I think. Like, I mean, at least when the mass ratios are very close to each other, one would expect that it should be more ballistic.
Yes.
In which case, it should have been a stronger divergence with system size, right? But here you find it's almost like Fourier behavior. Yes. So it's completely counterintuitive.
Okay, and no hand waving.
No, and it has been seen in some other models also, right?
But the universality scaling is the same for every mass ratio?
No, with scaling.
This 1/3 thing? Or
No, see, you can't see. You don't see the 1/3, right?
you don't see it yet.
So what is believed, at least I feel it should happen, is that you need to go to very long system to see again the 1/3.
To
But
see
it's
again.
yeah, but
So
it's
respect to, I mean, there is an article by Hurtado and must have been
sorry.
Hurtado and Garrido. I think he talked.
Oh yeah. So
Respect to their results. I mean, this is that.
right. Yeah. So
it does not confirm. It does not deny what
right. Yeah. So according to them, also it's kind of non-universal, right? That's their main argument. They do a different analysis to claim that alpha is non-universal, right? So in some sense, this is also consistent with that. I mean, they just do it in a more straightforward way. Like you just look at kappa versus n for different mass ratios, and you find like different powers. So it's also consistent with what they say. But now the main question is, like, see here. I mean, at some levels you can see it's going down and then going up, right? So I mean, I would believe that that's the general thing. Like it seems saturated and then go up. That has been seen in some other models. So that's what I would.
These are your simulations?
No, this is Casati and all these people.
And, they agree with Hurtado simulation?
No, so they don't do the kind of scaling analysis that Hurtado, but this sort of results are kind of they do actually much larger systems. This is like maybe 100,000 particles, so it's really huge simulations. But it's kind of consistent with what, in some sense, what Hurtado and you find through their different sort of scaling analysis.
Put that Hurtado and Garrido to that. They also find non-universal alphas.
Sorry.
Hurtado and Garrido also.
Right. Yeah.
It's non-universal.
Yeah. So they also, so that's kind of consistent, but yeah, it's not whether it's a finite size effect or so that's a big puzzle, I think.
If there are no other questions, we shall thank Abhishek again.
Okay, so there are no talks.